Now, for each type of gas molecules, we are going to study how many ways can these gas molecules move. So we start with monoatomic gas. So monoatomic gas again is molecules with only one atom in it. So we are going to study 3 different ways to move. First is called translation, followed by rotation and vibration. So translation, I believe you can recall it from mathematics. It's the motion of an object changing its position from one place to another place. Okay, in mathematics you learned before an object is at this point, this coordinate, how to move it by 2i, 3j plus 4k. Then you move the object into another point in space. So that one is called translation. Basically, it means an object move from one position to another position in space. Okay, so basically any kind of motion across space, you call it as translation. Okay, rotation is basically what you learn in chapter 6, rotation of rigid body, which involves an axis of rotation and an object moving around the axis of rotation. That one is rotation, this kind of rotation. Okay, vibration, it's similar to what you learned in oscillation in chapter 7. So vibration is basically a periodic motion with a specific relationship. So periodic motion is motion that happens regularly over a certain period. Okay, it happens regularly. So these are called vibration. Okay, so for monoatomic gas, we are going to analyze these three different types of motion to see how many ways can we move through translation, how many ways can we move through rotation, and how many ways can we move through vibration. Okay, for translation, I believe you are aware that there's probably 3 ways for you to move. The first way is having your particles moving in the left-right dimension. So moving to the right or moving to the left, that's the first way to move. So that's your first way. The second way will be moving either upwards or downwards. Basically, you're moving in the y dimension. So that is the second way of moving. Then the third way, I believe you know that our world right now, everything that we see right now is in 3 dimensions. So you have left, right, you have up, down. The next one will be front and back. So you can either move towards the front, moving towards you, or moving away from you, front or backwards. This is the third way for you to move. Okay, so from here you can see that the x-axis motion, we can call it by velocity x component of velocity, or the motion in the up-down direction, you can call it as y component of velocity. Whereas motion in the front-back direction, you can call it as a z component of velocity. So there's basically 3 ways for you to translate if you are a monoatomic gas molecules. Basically, I think any type of gas molecules, if you imagine it, it should be able to translate in 3 different ways, either left, right, up, down, or front, back. Any kind of motion, even though it is at an angle, if you resolve it, you are able to resolve it into these 3 components of velocity that we see here. Any kind of motion, no matter what angle, any orientation, you resolve it, is supposed to be made out of these 3 different components of velocities. Okay, next we move on to talk about rotation. Rotation, if you are a gas molecule, a monoatomic gas molecule, you basically have one atom only. So if you imagine it, the only way for you to rotate is to rotate like this. Okay, rotate like this, or rotate like this, or rotate like this. Okay, so if it's this kind of rotation, right, you see there's no significant motion of the particle. You don't see the particle move around. It doesn't displace from one place to another. It's just staying in its own place, rotating. So for this kind of rotation, right, actually it cannot store any kinetic energy inside this kind of rotation. Therefore, technically we can just call it as we have 0 ways to rotate, because all these ways that we mentioned earlier, technically they won't store kinetic energy inside. That's the easier way of imagining it. They cannot store energy inside because you don't see any significant motion of the gas molecules. Then of course, for vibration, if you have a particle that is undergoing vibration, even though if you think about it like this you might think of it as vibration, but if you look at it carefully, it's basically just particles moving to the left and to the right. So in this case, this vibration is actually just similar to translation. A single molecule, if it's vibrating, it's equivalent to it's just translating, because it's just motion to the left, motion to the right, motion to the left, motion to the right. So because of that, we won't consider vibration for monoatomic gas molecules. So we say that there's 0 ways to vibrate. Okay, so now we see that overall for monoatomic gas molecules, there's only 3 ways for you to translate, 0 ways to rotate, and 0 ways to vibrate. Therefore, we can say what is the degree of freedom of the gas molecule, means how much freedom in the way you can move. You can think of it like that. The technical explanation of degree of freedom is different, but you can think of it as how many levels of freedom do you have for monoatomic gas molecules to move is 3 degrees of freedom. You have 3 degrees of freedom for your monoatomic gas molecules to move. Okay, so moving on, you have diatomic gas, which is molecule with 2 atoms. Again, I believe you know that for any kind of gas molecules, there's ways to move left, right, up, down, and also front, back. But for rotation, it can be a bit interesting. Now, if you have a diatomic gas molecule, you can rotate. If you have your axis of rotation in the x-axis, you can rotate like this. If your axis of rotation is in the y-axis, then you can probably rotate like this. Okay, whereas if your axis of rotation is in the z-axis, then the z-axis is probably towards you or away from you, the axis of rotation, then you can see the gas molecules rotate like this. So technically, you can think of there's 3 possible ways for your diatomic gas molecules to rotate, but actually we only consider it to be 2 ways to rotate, because if you observe it, for the second diagram over here, you can see a clear motion of the particles around the axis of rotation. For the third diagram, you can also see a clear direction of motion, a clear motion for the gas molecules. But for the first one, this one in x-axis, is just rotation in its own place. You don't see any significant motion of the gas molecules. So that's why we can think that this first diagram here actually cannot store any kinetic energy in it. So that's why if you think about it, there's only 2 different ways for you to rotate for diatomic gas molecules. How about the vibration? The vibration here, there's actually 1 way for you to vibrate, which is as shown in the figure below, which involves the molecules getting close, getting far away, getting close, getting far away, getting close, getting far away. So technically, for diatomic gas molecules, there's 1 way to rotate. There's 1 way to vibrate, sorry. There's only 1 way to vibrate, but in our syllabus, specific for our Malaysia matriculation syllabus, doesn't apply to other syllabus. For our syllabus, we are going to ignore any vibrational modes. We are going to ignore any ways for it to vibrate, because technically vibration can only happen at very high temperature. Okay, higher temperature for what you need to rotate or to translate. Vibrate can only happen in very high temperature, and we are not going to discuss any kind of motion in that temperature. Therefore, we are going to ignore vibration in our syllabus. We are not going to discuss vibration in our syllabus. So if we remove the discussion of vibration for diatomic gas molecules, now you are only left with 5 different ways to move. 5 different ways to move. So your degree of freedom will now be equal to 5, and degree of freedom of 5 is for diatomic gas molecules. Okay, next you have your polyatomic gas molecules, which are molecules more than 2 atoms. Again, there's 3 ways to translate. You can also imagine there's 3 ways to rotate. But now, if you look at the first diagram over here, you can see that even though it's x-axis, you don't see your molecules rotating like this anymore. The molecules the molecules will be moving in space. Okay, because it's a non-linear molecule, it will basically rotate like this. It will basically rotate like this with the centerpiece remain in its place. Okay, so because there's motion across space right now, this axis of rotation, this kind of rotation can also store energy right now. That's why you can say there's 3 ways to rotate instead of 2 just now. Just now, if it's 2, it's because the 2 molecules are on the axis of rotation, so you don't see any significant motion. It's just like this. But right now, it's polyatomic, it's 3. So you can imagine it to be rotating like this. Okay, to be rotating like this, or to be rotating like this. Okay, so you can see significant motion of the atoms in space, so they can store kinetic energy. Okay, so 3 ways to translate, 3 ways to rotate. Well, actually, there's many ways for polyatomic gas molecules to vibrate. As you can see here, if this is a H2O, you can actually have 3 different ways to vibrate. But again, for our syllabus, we are going to ignore vibration. So if you calculate how many freedoms you actually have 6 degrees of freedom for polyatomic gas molecules. But there's a bit of a caveat over here. Actually, this discussion here for polyatomic gas molecules is only valid for non-linear molecules. Non-linear molecules means by the atoms that arrange to form the molecules are not arranged in one single straight line. As you can see here, the molecules here, there's a bend causing here to have a certain degree between the molecules over here. So the atoms are not arranged in a straight line to form a molecule. The atoms are arranged not in a straight line. So we call it as non-linear molecules. So example is like H2O. H2O, you know, there's a certain value, there's a certain angle between the hydrogen atom. Okay, so this is what we call non-linear molecules. And yes, for non-linear molecules, the degree of freedom is equal to 6. Okay, but actually there's a bit of caveat, because if you're talking about linear molecules, there's only two ways for you to rotate. Okay, let's try to study in deeper. Okay, polyatomic gas molecules for linear molecules. Right now we are going to talk about linear molecules. Again, you still have three ways to translate, but for the three ways to rotate that you see here, if you look at the first diagram, right now all these atoms are arranged in a single straight line and is passing through the axis rotation. So if you make it rotate in the x-axis, you see the atoms to be moving at its own place only. There's no significant motion like non-linear molecules anymore. So because there's no significant motion over here, technically this way will not store kinetic energy. Therefore, you're actually left with two ways for linear molecules to rotate only. Okay, so again, you ignore the vibration of linear molecules, but actually linear molecules, there's even more ways to vibrate, but we are going to ignore it. So how many ways do you have to move? Your degree is your degree of freedom for linear molecules is actually just 5. Your degree of freedom is 5 for linear molecules such as CO2. Why? Because one of the rotation here technically cannot store kinetic energy. Okay, my explanation here, it's a bit incorrect actually. I am simplifying things in a way that you are able to visualize it using diagram over here. But the explanation that on this axis you don't see it moving significantly, that's why I cannot store kinetic energy, that explanation is actually a bit hand waving. It's actually, there's a deeper explanation behind it, but for the sake of our discussion and for the sake of roughly understanding the idea, I'll be explaining it like this, but there's a deeper theory behind it that you can go study about it. Okay, so to summarize, monoatomic, your degree of freedom is 3. Diatomic gas molecules, your degree of freedom is 5. Whereas for polyatomic gas molecules, your degree of freedom is 6. We are not going to discuss linear molecules in our syllabus actually. So in our syllabus, we don't differentiate between linear and non-linear polyatomic molecules. We are going to just call them as polyatomic molecules, regardless whether they are linear or non-linear. So because of that, we are going to assume all polyatomic molecules to have 6 degrees of freedom. We are not going to say, oh, it's linear, that's why it's 5. We are not going to consider that in our discussion for our syllabus. But it's good for you to know that actually it's 5. But for our exam, any polyatomic gas molecule, how many degrees of freedom? It will be 6. Okay? So that's a discussion of how many ways a gas molecules can move. Then later in the next video, we are going to take this degree of freedom discussion over here and extend it to determine the kinetic energy, the translational kinetic energy, the average kinetic energy, and the internal energy of the gas molecules.